Hey everyone, welcome back to the channel. Today we're diving into a super important concept in statistics that sounds a little intimidating, but I promise it's not. We're talking about sampling distributions. Let's break it down. Say you work in HR and you want to estimate the average number of hours employees work per week, but your company has 5,000 employees. You don't have time to ask them all. Instead, you randomly pick a sample, say 50 employees, and calculate the average. That's called the sample mean, and it's our estimate for the whole company. Now imagine we repeat this process over and over again, randomly picking 50 employees, calculating the average, and recording it. Each time, the average might look a little bit different. Now we plot all those sample means, we get the sampling distribution of the sample mean. So a sampling distribution is the probability distribution of a given statistic, like the mean, based on a random sample. Now, this distribution tells us how much our sample mean might vary from sample to sample. If it's narrow, our sample mean is likely close to the real population mean. If it's wide, watch out. This is how we build things like confidence intervals and perform hypothesis testing. It's the backbone of inferential statistics. Now, one key feature of a sampling distribution is its standard deviation, also called the standard error of the mean. There are actually two formulas we will show here. Depending on the size of the sample, you're going to need one or the other. Question is, when do you use one or the other, and how does it all come together? Well, let's suppose there's a population that consists only of four numbers, the numbers 1, 2, 3, and 4. Now, let's try to do two things. One, get all possible samples of size 2 from the population, but without replacement. And two, get all possible samples of size 2 from the population, but with replacement. So this is what we have here. So we get the following pairs for number 1. So we'll get 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, and 3, 4 for a total of 6 samples that can be done out of a population of these 4 numbers taken 2 at a time without replacement. Next, we get the mean and the standard deviation of all the samples, and we come up with these 2 numbers. Note that the mean of the means, that is, the mean of the sampling distribution, is the same as the mean of the population at 2.5. Now, how do we explain the standard deviation of the sampling distribution? It turns out we can use the formula for small sample sizes as shown here. Note that with the formula and knowing the population standard deviation, we can compute for the standard error. Now, what happens if replacements are allowed? That means numbers can be repeated, and the samples are represented here in tabular form instead for easier presentation. With any 2 numbers selected, the resulting average is shown in the corresponding cell. And as before, we compute for the mean and standard error, like so. And here we show how the formula works in this case to see how to come around to the standard error given the formula. And it's just like this. Simple, right? Now let's have one more exercise, this time with sample size 3 and without replacement. So this is what it looks like. The only 4 samples possible are 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4. Now we get all of the averages and get the average of the average and the standard deviation of the averages, and we will have this. And notice that the standard error is smaller as the sample size goes up. How to use the formulas? When the sample sizes are small or they're sampling without replacement, we use this formula on the left. And when samples are big enough, or if it's small, but sampling can be done with replacement, it's considered big, and we use the formula on the right. A sample is often considered big enough in statistics when it reaches a size of 30. This threshold is widely used as a rule of thumb because it's the point at which the Central Limit Theorem begins to apply. The distribution of the sample means becomes approximately normal regardless of the population's original distribution, provided the population has finite variance. Now, caveat. The optimal sample size depends on the population's characteristics and the specific analysis being conducted. Larger or smaller sample sizes may be required depending on distribution symmetry, presence of outliers, and test sensitivity, etc. Also, in the presence of systematic bias in gathering the samples, a larger sample size will not correct for this survey bias. This is what happened in the Truman case. It's a classic example of systematic sampling bias where a large number size did not fix the problem. In the 1948 US presidential election, many polls and the Chicago Tribune newspaper predicted that Thomas Dewey would defeat Harry Truman. This prediction was based largely on telephone surveys, which introduced systematic bias because telephone ownership was not widespread at the time and tended to be concentrated among wealthier, more stable households who were more likely to support Dewey. Lower-income voters who were more likely to support Truman, on the other hand, were underrepresented in the sample because they were less likely to have telephones. This sampling bias, specifically exclusion bias, meant that the sample was not representative of the entire voting population. As a result, the polls were systematically skewed and failed to predict Truman's victory. Increasing the sample size would not have corrected this bias because the underlying sampling frame excluded a significant portion of the population. The erroneous headline, "Dewey Defeats Truman," famously illustrated this failure. So we have to pay attention as to how the sample will be generated. Okay, so if this helped you understand sampling distributions, hit that like button and subscribe for more easy-to-digest tutorials. You got questions? Drop us a comment below. See you next time!